Okay, good afternoon, everyone. Thanks for coming to today's general seminar. So today our speaker is Professor Hang Yu from Virginia Tech. He got his PhD from MIT. Essentially, that's how I got to know him from the graduate student socials. So that's why it's important for graduate students to have more social events to better know each other. Back when the time we were both at MIT, we were mostly working on thin film materials. But when Professor Yu has taken his faculty job in Virginia Tech, he has moved to the bulk material additive fabrication of metallic materials, especially with solid state approaches, something what he calls forging instead of melting. Through that direction, he actually attracted quite a bit of attention from the industry as well as the Department of Defense, because this is a very useful technique for metallic additive manufacturing. And he also worked with some people on machine learning to actually get better modeling of those fabrication process. So Dr. Yu also won the DARPA Young Investigator Award, which is a very high honor, very competitive for early career professors. And he served as an editor for the journal Materiala. So Dr. Yu, I think it's your floor is yours for the talk.
All right. Everyone can hear me okay? Well, thanks, Stephen, for the kind introduction. Thank you for the invitation. It's my great pleasure to be here today. I'm very delighted to use the next 50 minutes to share some of the work we did during the last few years on solid-state metal additive manufacturing and see how that may help us address some issues in the field of sustainability. Okay. All right, so the work I'm going to present was not done by me, right? Of course, it's done by my students and postdoc, current members and previous members who deserve acknowledgement in the very beginning. We also like to acknowledge some of sponsors for their long-term support over the last few years. All right, so I will start with sustainability, right? So everyone talk about carbon neutrality and supply chain challenges, and those challenges are pretty critical for all industries, and that's especially true for metal production. For a sustainable metal production, we need three things. We need low cost, we need short lead time, we need low energy consumption, low CO2 emission. Achieving those goals are not trivial at all, and I believe are not. So metal production accounts for 40% of all the industrial CO2 gas emission. And metal production can lead to significant material waste when you machine the material into the shape you want. And one extreme example is titanium alloys, right? Like folks in Boeing and Lockheed Martin, they started with the billets of titanium alloy and machine into the final parts. And during this process, up to 80–90% of the material can become waste. And the metal production can also take a long time because we have insufficient supply of large dies for forging and castings. And this can take up to a couple of years. So how can we address those problems? Let's look at the entire manufacturing chain of metals. Okay? You start from ores, you do extraction, purification, refining, right? You melt material, you add alloying elements, you cast them into ingots, you do thermomechanical processing, like rolling, forging, extrusion, and then you do machining, you get the final shape you want, right? This is a long manufacturing chain. But we can roughly divide that into two parts, right? The first part is primary processing and extraction. So for folks from the field of mining, extractive metallurgy, chemical metallurgy, this is their focus, right? And the second part is manufacturing. Right? So, and for my group, we're material engineers or mechanical engineers, right? So we're more interested in the manufacturing side. So we ask ourselves the question, right? What can we do to improve the sustainability of metal production from the manufacturing side, right? So look at this current manufacturing strategy. We have multiple manufacturing steps. There's a lot of energy consumption, and we have a lot of material waste. So what if we can have another manufacturing strategy so we can simplify the manufacturing steps and reduce the material waste? What if we can promote decentralized and localized production of component, so we don't have to rely on more centralized, like large manufacturing hubs. Okay. What if we can enable repair and remanufacturing? So when we have a large component with local damage, we don't have to throw them away, right? We can just do a repair, restore the geometry and properties, so we can extend the lifetime of a component, right? So all these bullet points point out to a new manufacturing paradigm, additive manufacturing. So what is additive manufacturing? Right, traditional, we do so-called subtractive manufacturing. So you start with a big chunk of material, like billet, and you remove material, right? By machining, you get a final shape. Additive manufacturing is opposite, right? You use building blocks, you add material, either layer by layer or voxel by voxel to get a final shape. So according to ASTM or ISO, there are 7 technologies for additive manufacturing. And based on those technologies, almost all types of material can be fabricated, right? So if you're interested in polymers, fused deposition modeling is very good for thermoplastics. And if you do a photocubable polymer, you can use material jetting or stereolithography. Right? And if you want to print metals these days, today, I would say the most popular approaches, or I would say the mainstream approaches, are the top 2, powder bed fusion and the directed energy deposition. And those 2 processes can be categorized as a common name like beam-based or fusion-based metal additive manufacturing. So in these cases, you have a high-energy beam. Could be a laser beam, could be electron beam, right? And you have a feedstock. Your high-energy beam selectively melt your feedstock. And as the beam moves away, your molten pool will solidify. So the initial powder will get together, bond together to become a solidified track. So your material pattern will be based on the traveling path of your laser beam or electron beam. So that's called a beam-based processes. So I have 2 examples here, like a small animation showing what's going on. So the first one is a powder bed fusion. So that's a layer of powder, and you apply laser. You can generate a pattern, okay, in this layer. And then you have to lay out another layer of powder. Repeat this process with a different material pattern, right, depending on your G code. Okay. Repeat this process layer by layer, you can make the 3D components. Yes. Of course, the material pattern in each layer does not need to be the same, right? That's why you make 3D components. Okay. But that's a very simple illustration. So this is a powder bed fusion. So you have a powder, you apply laser beam to generate a material pattern. There's another process here called directed energy deposition. So in this case, you have multiple nozzles. Right? So each nozzle supply a stream of powder. Right? At the same time, in the center, there's an infrared laser, apply energy to the location you want. So the material and energy come to the same space, same place at the same time. So you can deposit material to the locations you want. Okay. The cool thing about this is you can manipulate your powder supply rate. So you can do in-situ alloying, you can do functionally graded material here. Okay. So you see the 2 processes have very different configurations, but the underlying physical principle is the same. It's based on melting and rapid solidification. Right? So this is a fusion-based additive manufacturing process. It's pretty powerful, but it's not perfect, right? We have a lot of challenges now, actually. Because you have a small molten pool and rapid solidification, we're always suffering from the solidification porosity. You have such a high thermal gradient, we're suffering from high residual stress. And for some alloys, so-called non-weldable alloys, you have hot cracking problems, right? And of course, this is a high energy process, right? And you need to melt the material, so you need to heat up the material above the melting temperature. A lot of very high energy supply. And also, if your material is not perfect, you have porosity there, you have to do post-processing, like sintering or hot isostatic pressing to make it fully dense, right? And the cost is high, the powder is expensive, laser expensive, And also, I would say, if you want to have high-quality parts, your powder need to have a very stringent requirement. The powder shape and size distribution need to be meeting some certain requirement. Okay. So we wanted to solve the problem or solve some of the problem in the area of sustainability. But now fusion-based additives seems like give us more challenges, right? Because high energy and quality concerns. So what do we do? Well, maybe we should think outside the box, right? Not talk about additive anymore. Let's think about traditional box scale metal manufacturing. So how people do it, right? There are generally like two categories. You have so-called casting based, then you have thermomechanical processing based, right? The casting based is pretty good for large shapes, right? That's very difficult to machine. You can do casting to get large shapes. But if you want to have high quality and you have applications that require high load bearing capacity, you usually go to thermomechanical processing because forging, rolling, extrusion can help you get rid of the cast porosity, can modify the casting microstructure, can eventually lead to good mechanical properties. Like the example here showing airframes usually is based on thermomechanical processing. Right? So, but everything we talked about in the previous slide, right here, fusion-based additive manufacturing processes essentially are mini casting process. So of course you have all the problems you already have in casting, but things are worse because you have such a small molten pool, the thermal gradient is high, and the cooling rate is high, right? So the question then is, now we know thermomechanical processing, or say forging, can give me good properties. But now all the additive processes are based on casting. Can we have a forging-like additive manufacturing processes rather than casting-like additive manufacturing process, right? And supposedly we can inherit all the advantages we have in the forging, rolling, extrusion side and apply that to additive manufacturing, right? So that's a big question, right? And this question motivated our group to do some research during the last few years to figure out the answer. And the answer is yes, we can have a process based on, or like thermomechanical processing rather than casting, right? And this process is called additive friction stir deposition. Okay. The configuration of this process is showing here. It's pretty simple. If you're familiar with the polymer additive manufacturing process called fused deposition modeling, it looks very similar. You have a print head that is hollow out, right? And you have your feeder material going through that, right? So difference here is I need to deposit metal, right, which is hard compared to polymers. So I need to leverage some additional heating mechanism rather than just simply heat the polymers, right? So in this case, we leverage frictional heating. So what's going on here is I have my feeder rod going through my print head. And during deposition, both the feeder rod and the print head rotate very fast. Usually we talk about a few hundred RPM. As the feeder rod get into contact with the substrate, there will be frictional heating there. So the feeder material will get hot and soften. Then you apply compression, the material basically will yield and are extruded out to the side. Once the feeder material becomes beneath the printer head, okay, the printer head is also rotating, right? So the printer head can impose compression and shear further to plasticize the material. It's like a smearing process. So during this process, the feedstock feeder material, which is in the form of solid bar, will become fully plasticized because of compression and shear. Right? But not just the feeder material. Usually, the surface layers of the substrate also get plastic deformed and mixed together with the feeder material. So by doing this, you can get a really strong interface bonding. Once you have a good interface bonding, you can just move your print head based on G-code to generate the material pattern in the layer, and then you can repeat this process layer by layer. You can build a 3D components. Right? So that's a basic principle here. This is a small video showing what's going on, and the second is a thermal video showing the deposition process. Of course, the deposit material is getting hot. So I think in the rest of the talk, I'm going to show some features of this technology. I think I summarized 4 features. Right? First is the quality. You can get fully dense material in as-printed state. Second, properties. You can get forging-like mechanical properties in a convenient and inexpensive fashion. Okay. The third one is the circular economy applications. This process enables some cool applications like repair and recycling can further save energy. And last one is like the non-melting nature, low energy nature, and the flexibility about the feedstock. So I'm going to show how these features can help us address some sustainability challenges, lower the cost, shorten lead time, and lower the energy consumption and CO2 emission. So the first thing I'm going to talk about is the quality, right? So I'm going to touch upon a few things. Let's review the process fundamentals a little bit, thermal and deformation characteristics, and show you the full density in the acetated material and the interface bonding. Right, so like all the additive manufacturing processes, we have processing parameters, right? So for a laser-based process, of course, the laser power, the scanning speed are the major parameters. In our case, one major parameter is the rotation rate, how fast you rotate your printing head, right? Because that's going to have a significant influence on heat generation. Okay? Another thing is F, which is the feed rate, how fast you feed your feedstock. Velocity, V, how fast you move your printing head. And finally, of course, the layer thickness. Right? All these things will affect the physical condition in this process. So that's the empirical processing parameters. But we're scientists, we want to go beyond the parameters to properties, right? We want to have some intermediate steps, go from parameters to some physical conditions to microstructures to properties, right? So what's the physical conditions we care about? This is a deformation-based process, but also the material gets hot, right? So the two important physical variables we care about, temperature and strain rate. And this is not an isothermal process, of course, so you have a history of temperature. So what we care about essentially is a plot of temperature versus time. Another thing we care about is a strain rate versus time, right? So that's the two important things we care about, and we try to understand a quantitative correlation between the empirical processing parameters and the physical variables. From that, we can have some prediction of the kinetic variables and microstructure evolution. And from there, we can predict properties eventually. That's the hope. So in our lab, we have established a so-called integrated in-situ monitoring platform. So we have multiple sensors. We have 2 thermal cameras. We can visualize the temperature of the tool, the temperature of the deposit material. We have multiple thermal couples embedded into a substrate. We have optical microscope. I can visualize the material flow from the side. I also have, there's some built-in sensors, so you can get a sense of the torque and the force evolution during the process. Okay? And of course, there's other things like heat flux sensor or strain gauge sensors. So from that, we can try to understand how the processing parameters affect the thermal characteristics. Right? So one example showing is here is just from a thermal camera. So this is the deposit material deposition zone. This black thing is essentially my tool. I cover my tool, make sure there's no interference from the tool signal. So I just focus on the deposit material, and of course, we can measure the entire thermal field as a function of time. And this is an example of copper deposition. Of course, you see higher temperature of the material below the tool, and for the previously deposited material, the temperature will get lower because of cooling. Right? So we did this for a bunch of conditions, right? And another thing we can do is instead of looking at the entire field, we just focus on one spot, right? And monitor temperature change as a function of time. Then we can get a plot of temperature versus time. Like a typical curve, it would look like this. So what's important here is we can extract some important thermal characteristics from this plot. One important parameter, characteristic is the highest temperature during the process, called peak temperature. Okay? Another thing is the exposure time, right? Like how long the material is under the elevated temperature. Of course, the heating rate, the cooling rate are also important for us. Okay? So we did some kind of parametric study, right? Just one example showing here. Basically we kind of mapping inside the processing parameter space. We look at the aluminum alloy 6061 and the copper, and we linked the peak temperature with some so-called pseudo heat index, which is a function of my processing parameters, right? So this is just an empirical relationship, And you can develop that for specific materials. And for aluminum, we figure out omega squared divided by V is a pretty good empirical pseudo heat index, which is consistent with the previous work on friction stir welding. For copper, we figured out omega divided by V is a better term, and that's probably because copper has a very different contact state and the material flow behavior. So anyway, I think the take-home message is we can have a pretty extensive measurement of the thermal features during the process, and we generally can make the following conclusions. To ensure good deposition quality, the peak temperature needs to be high. It's below the melting temperature, but generally it's in the range of 50% to 90% of the melting temperature. Okay? Okay. The exposure time, we'll talk about this width. Like the material is under elevated temperature, it's usually on order of 10 seconds for typical deposition. Of course, it depends on what material, what condition you want to go. The natural cooling rate is on order of 10 to the 1 Kelvin per second. So it's pretty slow cooling compared to the laser-based additive process, which can easily give you like 1,000 or 10,000 Kelvin per second, right? Of course, we can increase this by some active cooling mechanisms. So that's about thermal. What about deformation? Okay, this is a pretty fast deformation process. Can we get some insights there? Well, we can do we can try to be smart, right, and do some innovative experiments. So one thing we did was a so-called tracer experiments. Okay. So our feedstock is a rod, right? Now we don't use a homogeneous material. We use an engineered feedstock. So we have a rod. This is the base material is aluminum alloy 6061, which is aluminum magnesium silicon-based alloy. We can drill a hole in the center. We put another aluminum alloy 2024 inside there, right? So 2024 is aluminum copper alloy. So the two aluminum alloy have very similar thermomechanical properties, so they can flow together during the process. Okay? But they have a different composition. They have a composition is like 5% difference in copper. So we can distinguish them using X-ray computed tomography. Okay? So during deposition, we have this essentially hybrid feedstock, okay, being deposited and stirred. And suddenly we stop everything, like stop action experiment, trying to freeze the shape of the tracer material, right? And then we can do in-situ characterization. Right? So in-situ imaging is pretty challenging, you know, in our lab. Maybe we will do in the future. We'll do some in-situ experiment in synchrotron. But at this moment, we just rely on in-situ experiments. So we do a stop action tracer experiments, and we get something like this, right? So the red and the purple, basically, that's showing you the tracer material. That is my 2024 aluminum. And in this case, the blue, and in this case, there's a transparent area. That's my base material, 681. I don't care about that part. I care about my tracer, right? So you see the tracer experiments start to develop this helical shape during the deposition, which is expected because you have downward feeding, you have rotation as well, and there is a rotation gradient between the top and the bottom of the deposit layers. Okay? But anyway, so we have done some detailed examination of the shape change, and we can estimate the strain inside there. I have to say the plastic deformation is history dependent, right? So you cannot just look at initial shape, final shape, make a conclusion. You need to really go to the intermediate steps. Okay? But I think for the sake of have a understanding of order magnitude, this is sufficient, right? So these are basically two sources of strains. One is compression as you feed the material. The other is torsion because there's a rotation rate gradient. The general conclusion is this is a large deformation. The cumulative strain is on order of 10 or above. And this number is consistent when you do a texture analysis to look at the shear texture of the material. So that's something we can probe from experiments, which is quite limited essentially. We look at thermal from in-situ perspective. We look at deformation from a stop action experiments. We can do more than that, just doing some process modeling, right? So, of course, this is not trivial either, right? So, but one easy way to model this process is to leverage the framework of computational fluid dynamics, right? So, because the material is going to have extensive flow under the printhead, we can model that as a fluid and get some insights there. So, basically, the three key equations will be conservation of mass, conservation of momentum, conservation of energy. So you can predict the steady state temperature and the velocity distribution. And you can validate the prediction with some experiments we have. So once the modeling has been validated, we can get some more insights that cannot be obtained from experiments. One is the material flow path, right? So, and we conclude that basically the material will have going down, and then you have kind of a spiral shape and flow path. Along the material flow path, we can record the temperature, right? Because we know the steady state temperature distribution. Now we know the flow path. We can do a kind of particle tracking, so we can get a history of the temperature and the history of the strain rate as well. So this is typically what we get. So the top one is a strain rate history. Initially, the material, once the material comes out of the channel, there's a high strain rate. Okay? Usually it's a short period of time. We'll talk about a second or so. And then the strain rate will decrease. Okay? For temperature, definitely the material, as long as the material is below the printhead, it's experiencing pretty high temperature. So there's an extended period of time that the material is under elevated temperatures. And this is consistent with what we find from the in-situ measurement as well. But I think the take-home message overall from the in-situ monitoring experiments and from the process modeling, we can say that this is a rapid and severe plastic deformation process in nature. It happens at high temperatures. It's below the melting temperature, but the thermomechanical history is pretty complex. It's not a constant temperature. It's not a constant strain rate. So this is some fundamentals of the process. What about the quality? Okay. Because we have intensive material flow, because we have compression and shear force there, essentially what we get from as-printed state is a fully dense material. So there's no porosity. We don't have to worry about porosity in the bulk of deposition. And that is a big improvement compared to the fusion-based process because you have solidification porosity, you have keyhole formation. So that's one unique advantage of this process, full density. Another advantage is the interface. This is again showing an example of a ice-printed material. We're trying to quantify the interface strength of the deposition. So we start with a very thick substrate of 6061 aluminum alloy. So this is about I think this is about we look at more than 5 centimeter thick substrate. Also, we deposit like hundreds of layers to get a very thick deposition. And then we cut a beam in the center. So I have a beam in the center here, right? So now my interface becomes the center of the beam. So then we generate a notch here and get a pre-crack by fatigue. We do a single edge notch bending test here, right? We want to see under this 3-point bending condition, right, how the crack propagates in the center, which is essentially my interface between the deposition and the substrate. Right? So this is what we get. So as you can see, the crack barely propagates along the center or the interface. Instead, we have a large plastic zone developed around that. And this is a sign of significant plastic deformation, right? So my interface is pretty strong, right? But I have to say I don't have a valid K1C measurement, right? Because my plastic zone is large compared to my beam dimension. So my beam is not small. It's not a micro scale. Essentially, it's a 10 centimeter long beam, right? But still, because the aluminum alloy has a relatively low strength and my interface is relatively strong, so we don't have a valid K1C measurement. But from that, we can semi-quantitatively say or qualitatively say that my interface is pretty strong. So that's a really good thing about this because the mixing and the cold plastic deformation, I got a good interface, and also we have fully dense deposition. Okay, of course, we have limitations as well, right? So what's our limitation? Okay. So this is a deformation-based process. As I explained earlier, right, I have a material getting yielded and being extruded to the side. So once the material is on the side, especially at the edge of the deposition track, the compression is low, and there's not much mixing between the deposit material and the substrate. So the edge is of low quality. Okay? So the edge of deposition has low quality, and sometimes you get pretty rough edges. So we have to remove those material. So those edges are called flash. Okay? So that's why we call this process, or it's better termed as near-net shaping additive manufacturing, because you have to remove some of the rough edges. Okay? When you deposit a large pattern, right, multiple tracks, you can try to reduce this problem by overlapping your tracks. Right? So I have this track and do overlapping. But in the end of the day, like the outer edges, you have to machine off materials. But that is, of course, much less significant compared to the traditional subtractive manufacturing process. But compared to the laser-based process, I think it's better term this technology as a near-net shaping process. Okay. So that's the first feature I talk about, right? So I think the take-home message is full density, good interface bonding, and near-net shaping. Right? The second feature I want to talk about is the forging-like mechanical properties. I'm going to talk about the microstructure formation and compare the difference between a laser-based additive manufacturing process versus additive friction stir deposition. I'm also going to show some examples of the properties you can get from 3 critical aerospace alloys. Right? So if you talk to the people from aerospace industry or Navy, or they say, okay, they only care about 3 alloys: aluminum 7075, aluminum 7050, and Ti64. So we're going to show you can get good properties using this process for these materials. So let's look at first to think about how the microstructure forms in the fusion-based AM process. So you have a molten pool and you have a substrate, right? And there's your interface provide heterogeneous nucleation sites. So heterogeneous nucleation is much more sufficient than homogeneous nucleation. So nucleation will happen at this interface. So the newly solidified material will adopt the crystal structure and the crystallographic orientation of the substrate. Therefore, you're going to have grains grow along the field direction. So you're going to get some columnar grains like this. And also because of, from knowledge from welding, we know for cubic material, 001 is an easy growth direction. So in the end of the day, you always have a strong 100 texture. Right? So naturally, you don't do anything, you get columnar grains with a 100 texture. Okay? That's not always what you want. A lot of time you want a more like a random texture, right? You want isotropic mechanical properties. So there's a lot of efforts trying to convert from columnar grains to equiaxed grains. Actually, that's not new knowledge. Actually, you look at welding literature, people already figured it out. There are 2 parameters that's important. One is the thermal gradient G. The other is the solidification rate R. So if you can have a relatively high R and low G, you can promote undercooling. So you can have a higher chance, better chance of homogeneous nucleation inside molten pool. By doing that, you can get equiaxed grains, right, rather than columnar grains. And this has been demonstrated by Operation National Lab a few years ago. They do an E-beam 3D printing, E-beam additive manufacturing of, I think it's nickel alloy. And to show that you can manipulate your processing parameters to control GR ratio, and so you can get some area columnar grains, some area equiaxed grains, right? The red means 100 strong 100 texture, and that's columnar grains. And then more like a greenish or non-red color, that is more like equiaxed grains with random texture. They can control that, so they can make a pattern like DOE, right, showing that. Another way to do it, right, so it's demonstrated by folks in the UCLA, UCSB, and HRL, is to add some nanoparticles. Okay? You add nanoparticles in your feedstock. Those nanoparticles have high melting temperature, can serve as heterogeneous nucleation sites inside the molten pool. So you still have heterogeneous nucleation, but it's inside the molten pool, so you can get equiaxed grain structure as well. Okay? So that's what people have done in the field of fusion-based additive manufacturing to control the microstructure. In our case, we don't have to worry too much about that, right? Because this is a deformation process at high temperatures. We have dynamic recrystallization, right? And depending on your material properties, right, you may have 2 types, so-called discontinuous dynamic recrystallization versus continuous dynamic recrystallization. Discontinuous recrystallization is more like a traditional concept. So you have a lot of dislocations, and there's a region you have a dislocation-free grain, and that grain can grow to consume the neighboring grains to reduce the stored energy, right? And then this new clean grain become big enough, you get a more dislocation inside. And you can repeat this process in a cyclic fashion. That's called dynamic recrystallization in a discontinuous way. Another possibility is commonly seen in the material with high stacking for the energy, in which case you have sufficient dynamic recovery. So during deformation, you're going to have dislocation wall formation to form subgrain structures. Okay? And then as deformation proceeds, the misorientation angle between subgrain will increase more. You become high angle grain boundaries to get continuous dynamic recrystallization. And if you remember, I just talked about this stop action experiments. We try to freeze the shape of the tracer, but also we can freeze the microstructure, the grain structure, right? So if we do that, we can map the microstructure evolution along the flow path to figure out the mechanism better, right? And this is an example of 2024 aluminum, which is a copper-based aluminum alloy. This is my base material microstructure. This is error 1, which is top in the print head. And you see there's not much difference, right? So there's not much good things going on. Error 2 is still in the channel, but right before the material come out of the channel. If you look at the microstructure, okay, a little bit of things going on, but not much. Right? Error 3 is right below the channel, so the material just come out of the channel. You see the microstructure, I got significant change. I got elongated and thin grains, right? And I can see a lot of gradient of the orientation angle inside the grains. I start to form subgrain structures. And error 4 and 5, basically after that, I already get dynamic recrystallization complete. I got equiaxed and smaller grain size. And if you will zoom in error 3, you definitely see more evidence showing that this is a continuous dynamic recrystallization. You have subgrains, and essentially the thickness of the elongated grain become the final grain size. And that's a mechanism specifically called the geometric dynamic recrystallization. So that's a piece of evidence showing that for some aluminum alloys, you have geometric dynamic recrystallization. But generally, for all the material we play with, we see some dynamic recrystallization. It could be a different mechanism. For all the aluminum alloys we play with, like 681, 2094, 775, it's all continuous dynamic recrystallization. For copper, we see signs of discontinuous recrystallization. And for titanium alloy, like Ti64, is more complicated because the deposition temperature is above the beta transits. So essentially, the material transforms to beta phase, and you have dynamic recrystallization to form equiaxed beta grains. And during cooling, the alpha phase will form inside the prior beta grains. Eventually, you get this laminar structure. Okay? But generally, you get some phase evolution or grain refinement in the deposit material. So that's about microstructure evolution. How about mechanical properties? How does our process compare to fusion-based process in terms of giving you good properties? So one example I'm showing here is a high-strength aerospace aluminum alloys. Those are 7000 series aluminum alloy. You have a hot cracking problem in the fusion-based process. So people in the field, and in the fusion-based additive manufacturing field, they add nanoparticles to address this problem. Okay? But for us, things are much easier, right? So we just use engineered alloy as our feed material, a deposit material, right? Fully dense, right? And then we do a solution treatment and aging. We get the right temper. We do a tension testing, and we can get comparable mechanical properties to a forging bar or a rod material. Another example is very similar but slightly different composition, 7050. Here, the story is similar. Right? You don't have to change any chemistry or composition or add nanoparticles. Just use the engineering feedstock. You can get good properties. Here, of course, I'm trying to show you a difference between the S-printed material and the aged material. The S-printed material is of low strength because there's a complex precipitous evolution during the process as well. And essentially, during the cooling process, there's overgrown precipitates, right? So you can see large precipitates, much larger than the ideal case, which will give you a peak strength. Okay? But after heat treatment, you can get forging-like properties. Okay? So of course we can make some kind of HP plot and see and show you that this process does give you probably falling in the regime of like a forging standard. I think the take-home message is this process, when we talk about high-strength alloys like aluminum aerospace alloys, give you a cheap and convenient solution to achieve mechanical properties, good mechanical properties. And this is the advantage, especially in this high-strength aerospace-grade aluminum alloys. And also we have demonstrated something similar in Ti-64. This curve is ice-printed material, because Ti-64 you don't have to do aging to get precipitates, right? So it's essentially a two-phase alloy. And we show that you can get similar mechanical properties in plane and also out of plane. Okay, that's pretty remarkable. And it's also fall into this regime of forging standard. Also, we try to understand how the strings depends on the prior beta grain size, or there's some relationship of that. Again, I think this part I want to give you the message that this process gives you a convenient pathway to achieve excellent mechanical properties, okay, compared to the fusion-based additive process. All right, so the third thing I want to briefly talk about applications. So what can we do using this process? Of course, it's additive manufacturing, but we can do more than just a manufacturing bulk scale component. We can do recycling and upcycling, we can do repair, and we can also try some austere conditions. Okay. So this is one example. So we get some machine chips, right, from Nissan. So Nissan have some cast aluminum alloy machine chips rich in silicon. Right? So we have machine chips, we just compress them into the same dimension of our feedstock. So it's a porous compact with a density of 68%. For this case, we don't have to do any sintering. We just have a porous compact. We insert that into the channel. We do a deposition. Right? And it turns out we can get a fully dense material. Even the feedstock is not fully dense. Well, this is because we have sufficient material flow, compression, shear. So there's some in-situ consolidation process. Right? And then we can, of course, again, I show you there's some rough edges, right? So we can remove those things, remove those things, and we get a block. We can fabricate a tensile bar, okay, and test the mechanical properties. This is ice-printed material, right? No heat treatment. This is what we get. Okay. So the red is the original bulk scale cast aluminum alloy. It's brittle because you put a lot of silicon there to improve the castability. So silicon really, the large silicon particle kill the ductility. But after deposition, our material become more ductile. Essentially, you see significant strain hardening. So why is that? Right? If you examine the microstructure and compare the feedstock material, which is machine chips, versus the deposit material, you'll see the secret. Of course, we have grain structure change, right, because dynamic recrystallization. But more than that, more importantly, we also have a second phase particle change. In the original cast aluminum alloy, I got large silicon particles, elongated. I have also iron-based intermetallics. But during the stir process, because of the shear force, I'm actually breaking those large particles into small pieces. And the particle become more spherical and well dispersed. So now this microstructure gives me better ductility and also some strain hardening behavior. Right? So overall, what I did, not just to consolidate the material, at the same time, I changed the microstructure during deposition so I can improve the ductility. Right? So we show this work to Nissan people, and they say, oh yeah, you should call this upcycling rather than recycling because you improve the ductility and energy dissipation. Another application is repair. Okay? So when you have a large metal components, you can always have local damage like surface divot, you have trenches, you have some missing features or cracks, right? What do you do with them? Okay. You want to repair them, right? Rather than just throw away a big component with local damage. How to repair that? So in this case, we want to do structural repair as opposed to so-called cosmetic repair. So structural repair means I want to repair the geometry, at the same time also get good mechanical properties. Right? So we survey different repair technologies and divide them into 4 quadrants. Depends on whether melting happens or not, whether technology is additive or not. And our conclusion is we want to be in quadrant 3. We want to have a solid state, non-melting process, but additive, right? And there are two options essentially at this moment. One is additive friction stir deposition, the technology I'm talking about. The other is cold spray. And you know, for your background, Navy has invested a lot of fundings on cold spray over the last decade or so. Cold spray has demonstrated great success for surface repair, but for deep holes or deep volumetric damage, additive friction stir deposition is your choice. So here's an example. Okay, well, I don't know if you can see this, but this is a hole here. This is a hole, through thickness hole of a 1/4 inch aluminum alloy plate. Our process demonstrates that you can actually deposit material into the hole. Not just deposit material, essentially you're pushing the material into the hole. There's going to be a mixing and interaction between the deposit material and sidewall. By doing this, you can get a good interface bonding. And we show that for a 1/4 inch thick plate, through thickness hole, we can actually fully fill that. Okay? You can see the backside, you know, the material is fully filled. And we showed that to some Navier people in 2019, and they said, okay, we have actually a project for you to think about. Turns out Navier suffer from corroded hole problem for long term. So the big airframes, you have a lot of holes for fasteners. And during service, you get corrosion all the time. So the corroded material is surrounding the hole. You have to remove the material so your hole becomes bigger. The fastener won't fit. How do you address this? The current strategy is essentially fabricate a bushing structure, like a ring, just mechanically insert into that. The airframe is made of aluminum 7050, and the ring is a stainless steel. Making the ring is also actually time-consuming and expensive. But also, you don't have a you don't have a bonding between them. It's just a mechanical interlocking. Also, you have a sharp interface. So that's another option, good option. So, and this project is based on the idea now we can fully fill how maybe we can apply that to address this problem. If we can be successful, we can shorten lead time, reduce the cost, and could possibly repair this multiple times. Okay. So quick illustration of what we did. We started with a larger hole after we removed the corroded material, and then we fully fill the hole using additive friction stir deposition. We're going to have, we need to develop some recipe, right? Some deposition processing recipe, deposition path to fully fill the hole, make sure there's no defect or kissing bound like this. And then we can remove the excess material and re-drill the original hole size. Yeah, so eventually we can fabricate them into fatigue tested testing coupons. And you know, of course, it's fatigue testing. We need to take care of the statistics, right? We have to make tons of coupons to make sure everything is consistent. And those are some examples we make. This is after deposition, so you have small caps on the top, and then remove the excess material, re-drill original hole size. I got 10 plus fatigue coupons I can test, right? So I think I'm not allowed to show you all the detailed data, the curves, but I think I can give you the qualitative description of what's going on, right? So when you have a pristine material, you do the fatigue testing with a hole, eventually your crack will propagate in the horizontal direction because the tensile stress, right? If you do a good repair, like this, we develop a recipe, we also get the same failure mode like this. Okay? So we can actually get a comparable or even better fatigue performance than the base material because actually we changed not just the repair, the geometry, but also we changed the microstructure of the deposit material as well. I don't have time to go into detail, but it does relate to crack initiation mechanism and the crack propagation mechanism. Okay. All right, so if you don't do a good repair, you're going to fail at the repair region. You have a bowl shape. So, but I think what we can say is we have developed a recipe. We can get good repair performance. Last thing I think I want to show you quickly is this process can be applied in the water, and we show this possibility, and we won a American-made challenge by DOE, so there's a prize together with my students. I used to have a video to show you. I think I'm running out of time. I just skip this, but I think the take-home message is we can go from waste to part. We can restore geometry and performance, and we can apply this to some austere conditions. The last thing, I have 3 slides, I think, left over. Let's go this quickly. So what's the last feature here? It's a non-melting process, right? So it's low energy. But also, I'm so flexible about the feedstock. You see, we can use any solid bar, any even recycled material, right? And also, I want to show you this is a scalable process and talk about energy input. So in the fusion-based additive process, you need powder, and powder is expensive. Takes time and money to make high-quality powders. For our case, we don't have to. If I have a foundry, right, cast me a solid bar, I will do a printing for you, right? So we can, it's fully compatible with casting. We can try different alloys of interest. We can arbitrarily change the composition and play with that, right? You don't have to make a powder first. And also, because the deformation process nature, you can control the grain size, control the precipitates. By controlling the processing conditions, you can make some functionally greater material in the future as well. This process currently designed for large scale. So the feedstock I'm talking about has a dimension like a centimeter by centimeter. Right? So it's large. You're not going to make an Eiffel Tower like this big using this process. You're going to make big things, right? So, and there's some few examples, and those are really meter scale. One thing I want to mention is the Army is really interested in this, and they are trying to build, I think they're already finished, building this world's largest metal 3D printer in Rock Island Arsenal, Illinois. So the idea is very simple, using the same print head we have, right? But they build a huge gantry, so you can move the print head X, Y, Z. You can get 30 feet long, 36 feet long, 25 feet wide, and 13 feet tall. So we're involved in some project with them, trying to figure out some cool project for the industry. So last thing I want to talk about energy, right? So turns out energy input is relatively low. So the vertical axis is essentially the energy cost per mass. We're talking about kWh per kilogram. So turns out if you have a relatively low rate, you can be in a regime of 4 kWh per kilogram. But if you increase deposition rate, you can lower the energy input per mass. Okay? And that's very impressive compared to the traditional manufacturing process like ingot casting, extrusion, or ship casting. So this definitely gives us a low energy path to move forward for a more sustainable future. So again, the last feature, I think the take-home message is robust technology. I can use feedstock by casting or by waste material. It's scalable and relatively low energy process. So this is like a summary slide. We have talked about 4 features, how that to link to the sustainability. I'm sure all you guys have an answer already. Right? Think about, quality, defect-free. You don't have to do post-processing to eliminate the porosity, right? Lower the cost, energy consumption, forging-like properties, right? Easy to make. Also, of course, lower the cost and lead time. Circular economy applications, recycling, repair, definitely good for cost and energy CO2 emission. And the flexibility of feedstock, non-melting nature can overall improve the sustainability, right? So my last slide here is a summary of this process. I think, it's worth mentioning, what I talk about today is really the basics. I think there's a future vision of that. There's a few directions, including more understanding on the process physics, and there's some innovation of material. You can make hybrid material. And there will be AI-related combined physics with AI for prediction and control. So with that, I will stop here and take questions. Thank you for your attention.